Hi everyone, welcome to Savvy Education. Today we are diving into the fascinating world of probability with a classic problem, the Monty Hall problem. If you are not familiar, the Monty Hall problem is a brain teaser based on a game show. You are presented with three doors. Behind one door is a car, and behind the other two doors are goats. The game show host Monty asks you to pick one door. Let's say you pick door number one. After you pick a door, Monty opens one of the other two doors to reveal a goat. You are then given the option to stick with your original choice or switch to the remaining unopened door. The big question is, should you switch or stay to maximize your chance of winning the car? Now, we are not going to write a bunch of formulas and try to prove anything theoretically, which even I don't understand a bit. Instead, we will be using actual programming and write a code in Python to run about thousands of iterations and see the practical result. Let's get started. We start by importing the random module. Then we define a function, Monty Hall, with two parameters. First one will be selection, that will be of type integer, and second one will be decision, that will be of type boolean, and this function will return boolean. Now we will create three doors, that will be a dictionary of type integer as a key and string as a value. Of course, which door has which object, that will be defined randomly. So we will remove the objects from here and create another list of objects. That will be a list of type string. Now using the random module, we will shuffle the list of items and assign those to individual doors. Now if we were to run this, we will simply print what's behind each door, and here we will call a function with random parameter. We can see every time each door gets either a car or a goat. Great. So far so good. Now comes two conditions. If the contestant decides to switch or stay with his original choice. Now let's look closely. If the contestant decides to stay with his choice, it doesn't matter if Monty opens the door with a goat or a car. If the chosen door has a car, the contestant wins, and if it doesn't, the contestant loses. So coming back to our code, if the door with user selection is equal to car returns true, means contestant wins, else return false, contestant loses. Coming to the scenario where the contestant decides to switch to the remaining unopened door, we know that the door Monty opened has a goat, which means one of these door also has a goat and the other one has a car. Here we can deduce that if the contestant had originally chosen the door with a goat, upon switching he's gonna win the car. And if the contestant had chosen the door with a car, upon switching he is going to settle with the goat. So we can write, if the door with user selection is equal to the car, return false, means contestant loses, else return true, contestant wins. Now that we have our function ready, let's call the function with appropriate arguments. Now we will create two lists, one to capture simulations when the contestant sticks to his original choice, and one to capture simulations when the contestant switches his choice. Let's set the number of iterations to 1000. Now loop through the iterations. Every time the contestant will select a door from 1, 2 and 3 at random. And finally call the function Monty Hall with argument as selection and decision, which will be false if the contestant chooses to stay with his choice. Lastly, append the result from the function to the list of results. Similarly, we can loop through the iteration for the scenario where the contestant decides to switch to the different door. So here the decision argument will be true and we will append the result to the second list. Now let's print the results. Here we will write a print statement with an F string. Success rate original is sum of list of original results divided by length of the list and multiplied by 100. Copy the print statement for the results from the switched list. Alright, let's run the code and see the results. As you can see, the success rate when switching the choice is around 65% and when not switching is around 34%. Let's run it once again. Again, success rate when switched is around 68% and when not switching is around 34%. Just to be sure, again, success rate when switching is around 67% and when not switching is around 32%. The Monty Hall problem is a great example of how probability can sometimes be counterintuitive. Using actual programming and performing thousands of iterations, we practically prove the theory that you are better off switching doors. Thanks for watching. If you enjoyed this video, give it a thumbs up and don't forget to subscribe to Savvy Education for more interesting programming content.